Hi everyone, my name is Rajat Kumar. I'm a man with whitish complexion and black hair. I'm also wearing a blue shirt. Uh, Today I will be presenting our work titled Intent Detection and Discovery from User Logs via Deep Semi-Supervised Contrastive Clustering, in short as DSSCC. This is work done with my colleagues Mayur Patidar, Vaibhav Varshney, Lovekesh and Gautam Shroff at TCS Research, New Delhi. Consider there is an intent detection system which is trained on existing set of intents. Now, when users interact with the system will only reply to those queries which are classified correctly by the system and with high confidence. Okay, and the low confidence queries will be saved to a database for further analysis, which are called user logs. The domain expert will be annotating these queries manually, which requires extensive human effort. Now, there are three classes in which the user logs will be classified by the domain expert, which are existing intents, uh, new intents, and out of scope queries. Okay, and retrain the model with new intents. Okay, so in our work, we propose both a fully automated and semi-automated system for annotating user logs with significantly less human effort. So we formulate the problem setup as shown in figure. Given very few labeled utterances from known intents and large volume of unlabeled utterances from both known and unknown intents, the idea is to classify or cluster the unlabeled data from both known and unknown intents. In the literature, there are mainly three broad categories. First is like self-supervised deep clustering. In these papers, contrastive learning is utilized to update representations either at the instance level or at the cluster level. A number of clusters or intents are assumed to be known a priori. Cluster centers are updated either via KLDIV loss between auxiliary and target distribution over intents or contrastive loss at the cluster level. Usage of pseudo-labeled data is also seen in the approaches. Low accuracy on pseudo-labeled data or incorrect auxiliary target distribution may lead to cluster degeneracy. Second category is semi-supervised deep clustering. These approaches try to utilize labeled data as well as unlabeled data for updating the representations. Deeper learned employs representation learning and clustering in an alternative fashion. Incorrect cluster assignment over epochs or incorrect estimate for M or the number of unknown intents may lead to low cluster accuracy. The third category is unsupervised clustering plus human effort. So these approaches model intent discovery from unlabeled utterances as an unsupervised clustering problem and propose a variant of DB scan for clustering. The problems with this approach is like this approach does not employ any representation learning and rely heavily on manual evaluation. So what if we have some approach that utilizes both labeled and unlabeled data for updating the representations as well as requires minimal human effort and gives better performance. So this is high level overview of DSSCC-E2E. E2E stands for end-to-end approach where we perform automated intent detection and discovery. This is a two-phase process. We assume the total number of intents are either known a priori or estimated by an existing algorithm. So this is phase one of DSSCC E2E. Okay, we fine-tune the PLM uh, by minimizing the cross entropy loss over label utterances from known intents. So in phase two, this is semi-supervised contrastive representation learning. So for contrastive learning, we need augmentations. And for implementing semi-supervised setting, we will utilize neighbors from same class as augmentations for labeled data. And for unlabeled data, we use contextual augmentations as shown in this figure. Okay. So for a given pair of utterances which belong to the same intent, we minimize the distance between distribution over intents. In phase 2, for maintaining the accuracy on known intents, we also use label utterances to update PLM representations via cross entropy loss. We add one more term to the final objective function, that is entropy maximization term, to alleviate the issue of empty clusters. So as we can see, this is the final objective where we minimize the semi-supervised contrastive loss and the supervised representation learning loss and maximize the entropy term. So this is the experimental setup. For the semi-supervised scenario, we assume a percentage, X percentage of the total intents are known a priori, also referred to as the known intent ratio. For niche known intent, 10% of the utterances are labeled and the rest are unlabeled. We have experimented with 5 publicly available datasets with a variety in total number of intents. Banking and Flink contain 77 and 150 intents respectively, whereas other 3 datasets are having number of intents less than 20. This slide shows the comparison with other unsupervised and semi-supervised approaches, with BERT base as the common PLM for fair comparison. As we can see, DSCC clearly outperforms all unsupervised baselines by significant margin. Also, DSSCC outperforms semi-supervised baselines on banking and Cling for all cases except for an MI metric on the Cling dataset for KIR 50 and 75%. Now the question arises, what if we use a different PLM for this task? And what if we use Espert, Reimers and Grubich 2019 as PLM? So we compare only DeepAlign and DSCC here, as DeepAlign was previous SOTA. As you can see, DSCC Espert outperforms DSCC BERT, DeepAlign SBERT and DeepAlign BERT by significant margin on both datasets for all evaluated intent ratios. So the utterance representations from SBERT are more suitable for clustering than BERT-based representations. These are the results with 3 other datasets, SNP, Stack Overflow, and DBpedia, with fewer number of total intents. DSSCC outperforms DeepAlign on 3 datasets except for NMI on DBpedia for intent ratio of 75%. These results are for the scenario when the number of new intents M is estimated using a heuristic. The estimated M is used for intent detection and discovery with KIR 75%. So here we use an existing algorithm proposed by Zhang et al. 2021, which refines an initial guess K dash to arrive at the final estimate K pred. DSCC outperforms DeepAlign except for the NMI metric on Clink 150 dataset for K dash is equal to 450 and K dash is equal to 600. All the results are competitive. Performance of DSCC last row does not drop significantly even when the total number of intents in user logs are not known in advance. So existing approaches including our variant 1, which is DSCC end-to-end, require an estimate of the number of new intents M present in the user logs. An incorrect estimate for M leads to noisy clusters, and in that case final clustering output requires splitting noisy clusters, which requires extensive manual effort. So we decided to propose a variant 2 of our approach, which does not require automated estimation of the number of clusters. So there are 3 phases in this approach. So given existing intents data or known intents data, this approach does fine-tuning similar to phase 1 of DSCC. And for phase 2, given user logs or unlabeled data from known and unknown intents, DSSCC-HIL performs representation and learning and clustering in an alternate fashion and uses DBSCAN to generate dense and pure clusters, which are large in number. So for phase 3, domain experts merge the clusters with minimum manual effort such that each merged cluster represents an intent. Then a classifier is trained on this data and prediction is done on test set. Note that merging clusters is an easier operation than splitting and can be performed with minimal manual effort. So this is phase 3 of DSSCC-HIL, which is cluster merging algorithm. So given a large number of dense and pure clusters, multiple clusters may belong to the same intent, and we use manual effort to merge similar clusters based on nearest neighbors. In each iteration, a domain expert is shown 5 candidate clusters, which are nearest neighbors of query cluster Q, where per cluster only 2 utterances are shown to the expert, and based on the reply from the domain expert, some candidate clusters are merged into the query cluster, and the cluster definition is updated. After cluster merging, we treat each cluster as an intent and train a logistic classifier to label utterances that belong to the outlier cluster. We use the same classifier for intent detection on the test set. So let's have a look at the results of DSSCC-HIL as compared to our own end-to-end approach. So we compare DSSCC-E2E, E2E plus HIL and HIL, and P and Q here refers to the average cluster initial average cluster purity before merging and the number of queries respectively, which are required by a domain expert. Here we have used Oracle ground truth cluster labels instead of a domain expert to answer queries asked during a cluster merging algorithm. DSSCC-HIL achieved an accuracy of 81% and 88.93% on banking and Flink respectively, which is significantly higher than DSCC end-to-end approach. Also, DSCC-HIL is able to discover all intents in the ground truth. We also employ a cluster merging strategy with DSCC-E2E, which is DSCC-E2E plus HIL, and got an improvement of 2% on Flink, but negative results for banking due to low initial cluster purity. So now concluding our work. In this work, we propose a semi-supervised contrastive learning approach for intent detection and discovery from user logs. The proposed approach optimally utilizes both labeled and unlabeled utterances and outperforms SOTA approaches for both scenarios when the total number of intents is either known in advance or has to be estimated. We also propose a variant of our approach which does not need to estimate the number of new intents and yields pure clusters which are merged by domain expert based on the cluster descriptions. So future work will focus on how to get better cluster descriptions, how to optimally select query and corresponding candidate clusters, and how to discover new intents with minimum human effort with a long tail distribution over new intents in user logs. So that is our work. Thanks for listening. Thanks.